Good morning, dear students. Welcome to this class on prestressed concrete. We have completed the types of failures in case of prestressed concrete under flexure. Uh, Now we will see uh, the code procedure for finding flexural resistance of a prestressed concrete section. Okay. So, in the other way, moment of resistance value how to calculate. Okay, all that. Right. You can see this diagram, which you know very well. Uh, it is like stress block parameters we are going to talk about. So here you see a rectangular cross section with some no tendons placed at this location. The rectangular cross section dimension B and effective depth is D, not the overall depth, capital D. So the terms remain same what you learned in RCC. Capital D means overall depth of the beam from top fiber to the bottom fiber, whereas small d is effective depth, which is the distance between the topmost compression phase to the location of steel, right? So this is effective depth and the width of the section, area of pre-stress, cross sectional area, and you can see the stress block parameters to the right of this diagram, where FPU in the sense characteristic strength of steel, area of steel. If you multiply, you will get tensile force. Okay. What do you get from this? Stress into area is a force, nothing but tensile force, because what stress you have here is tensile stress. Similarly, stress block, it is parabolic, till uh, this point, and then it is a, constant value, straight line, parabola and combination of a parabola and straight line. Okay. Now the straight line portion is 0.42 xu, and now if you can calculate the area of this stress block, that will give you 0.36 fck b into xu as the compression force. Okay, so compressive force is this much and tensile force is this much. The lever arm, if you see the distance between the tensile force and the compressive force, this is the lever arm. Overall depth is d minus this value. If you do, you will get the lever arm value, which is a 0.42 xu is the lever arm value. Okay, so to get the tensile force which is acting towards right and the compression acting towards left, both are trying to develop a moment value. So that is what is called moment of resistance. These are all internal, developed in the pre-stressed concrete member. The tensile force, compressive force, and the moment out of that is developed. That is what is called moment of resistance, which will resist the bending moment coming from the loads. Okay, right. So these are all from the materials that you are using. Steel is developing some force which is tensile. Concrete is developing some force, that is compression, and both are together is developing some moment that will be resisting the moment from loads. Okay, right. We will see now the formula, that is the just force multiplied by the lever arm will give you the equation for moment of resistance. And you need not remember this stress block. It is already available in the IS code. We have seen, and figure 4 in the IS code will give you the stress block parameters. Okay, so this is how it is, right? And now you can see this formula is taken from the code, so notations will be little different. Textbook use FPU for FPB as code. Code use FPB, F suffix PB, whereas textbook use F suffix PU. Okay, right? Tensile stress in tendon at failure. Okay, so that is FPB into area of pre-stress, capital A, into D minus 0.42 XU is this value of MU, which is moment of resistance. Okay, got it? So as I said, FPU, this is taken from textbook, this diagram. So it uses FPU and AP as symbols, notations, whereas the IS code, this formula is written from IS code. So this is available. You don't need to remember this formula. It is available in Annexure D, page number 51 of your IS code. Okay. So mu is equal to FPB APS A suffix PS D minus 0.42 XU is the lever arm value. D minus 0.42 XU is like lever arm. Okay, so force multiplied by this distance is moment. Okay, so FPU AP D minus 0.42 XU according to textbook. Okay, right? So this is the formula, and as I said, D is the effective depth to the centroid of the steel area, and XU neutral axis depth. Okay, right? FPE, which is effective pre-stress in tendon, and mu, moment of resistance of the section. Right, for pre-tension members and post-tension members with the effective bond between concrete and tendons, value of FPB and XU are required, and those are given in table 11 of your IS code. So to use this formula, what you want is FPB, okay, and XU value you want, because the area of steel will be known to you, because you will know number of tendons and the tendon size. Okay, all that, and you know effective depth of the member you will be knowing, because you know the cross section of the member, and you know where the tendons are being provided and how many number and all. The area is given to you, area of pre-stress. Okay, uh, to know the tensile stress in tendon at failure, this is what you want. Only what you know is FP value, where no effective pre-stress will be known to you. The characteristic strength of steel will be known to you. Okay, so that's why you will have to calculate what is FPB and XU. So that is given in table 11 of your IS code. Okay, and you know this point we have seen already. The effective pre-stress after all losses is should be not less than 0.45 times of FPU. Okay, FPU is nothing but characteristic tensile strength, right? And this is one more condition: pre-stressing tendons in compression zone should be ignored in the strength calculations when using this method. Okay, so pre-stressing at sometimes you will have tendons in compression zone also sometimes, so you have to neglect these tendons in this calculation. Only whatever are below neutral axis, whatever provided tendons provided below neutral axis, you shall take into account. Okay, So now this is what I was talking about, table 11. Okay, to use into that equation. So how you read or get FPB value and XU value. Okay, so for that what you need is this value. Okay, as you can see, stress in tendons as proportion of the design strength. Okay, and now ratio of depth of neutral axis. So these two values you can read it from this table only when you know this value. What is it? Area of pre-stressing tendons, you know it. FPU, what no, is the characteristic strength of steel will be given to you or known to you. B, width of the section. D, effective depth. FC, grade of concrete, or nothing but 28-day characteristic compressive strength of concrete. So these are all known data. So once you get a value, say if you got 0.1, okay, and if it is pre-tensioning member, so you have to take this as 1 is equal to 1. So you know FPB can be calculated 1 into 0.87 FPU. What is FPU again? Characteristic tensile strength of tendon will be given to you. Maybe 1000 megapascal, 1200 megapascal, 1600 megapascal. Likewise, similarly, XU by D value can be read from this, say if it is pre-tensioned. So 0.217, nothing but which is equal to 0.217. So what is XU? 0.217 into D. Okay, right? So that is how you get XU value and FPB value, and substitute in this equation along with all other parameters D and all, you will get MU value. That is simple to calculate MU value for a rectangular section. And T section, rectangular section, T section for which neutral axis lies in the flange. So there are three things you can categorize here, the moment of resistance. One is for rectangular section. This is one thing, rectangular. Another one is like flanged section. I don't say T section and all. I just say flanged section. Okay. So where the neutral axis lies in the flange, neutral axis in flange. Okay. This is that case. And the other one is also flange section where neutral axis in the web. Right, this is another case. So first two cases, rectangular section and flanged sections like T section, I section, L section, C section, all are flange sections. So where neutral axis falls in the flange itself, this formula can be utilized. Okay, and this formula is not suitable for the third case. What is it? Flanged sections with the neutral axis in the web. Okay, so most of you will know all this terminology. Neutral axis falling in the flange, neutral axis falling in the web from your RCC. It's very similar to that terminology. Okay, right. So table 11 is available in annexure D of your IS code. I'll just show you if you want. We'll just open the IS code. So you just keep open the IS code along with me. So I told you to have a copy of IS code along with you. It is always required The IS codes are very much required when you are going for the designs of the particular sections. Okay, right. Annexure D, we shall go. So this is annexure D, as you see, page number 51. So this is annexure D, where it talks about only moment of resistance for rectangular and T section, something like, I mean, mostly the flanged sections. You see this formula, whatever I have presented is here, and the table you see, whatever I have presented, it is available here. Okay, right? So you don't need to remember anything, just you need to know where it is available and how to use it. Okay, that is what you need to know. Right, coming back to this table again. So you have to calculate this value in this second column, uh, a suffix ps fpu divided by bd okay, so once you know this value, then you can get fpb value from this and xu value from this. Okay, accordingly with that pre-tensioning or post-tensioning, and you need not worry about the bond, whether it is having bond or unbonded. Earlier code like is 1343 1980 used to give two tables, where for bonded one table and unbonded the other table. The revised code doesn't give a separate table for unbonded pre-stressed members. Okay, right. Coming to the third case, what I was telling, like moment of resistance of flanged sections in which neutral axis lies outside the flange. I mean web, in the web. So how you deal with this? So just split the stress block into two, one for flange, exclusively for flange, another for web. Okay, and as I said, just split this into two diagrams. Okay, one is this one, something like this. So this is one, total is one, and this is two. I mean, complete another rectangle. So make this into three rectangles. Okay, so this the stress block parameters corresponding to this is this one, and stress block parameters corresponding to the web are like this. Okay, so this that is how you have to read it. Okay, you know very well from RCC, you might have already done this, but once again. Okay, so as the stress block is extending beyond the flange, so it is taken as rectangle. Stress block is rectangle for this portion of flange. Beyond that is parabolic anyhow. Okay, but exclusively if you are talking about flange, so stress block will be a rectangle. Whereas for this diagram 2, it is both parabolic and rectangle. Okay, so till this it is a rectangle, and beyond that it is parabolic. Okay, so this is how you have to split it up, and you have to split the parameters also. Say stress in steel, FPU, and APW. Okay, area of pre-stress in web. Okay, right, అట్లాగే I mean FPAPF flange. Okay, XU is again the same old notation. 0.42 XU is the no, depth of compressive force from top. 0.45 FCK is the no, the compressive stress after all no, applying the material factor of safety of 1.5. Okay, so 0.67 FCK is the the FCK value which is allowed, and for that again you have to apply 1.5 of material safety factor, which will give you design stress value. This is from stress strain diagram of concrete that we have already talked about. It is also available in the IS code 13432012. Okay, right. Now you can see this is 0.45 FCK. Okay, B minus BW. This is total B minus BW. This is BW. Okay, so B minus BW is the uh, width and DF is the depth. So that is how you get the area, total area of this portion. Okay, and remaining is this one. Okay, so 0.45 FCK into B minus BW into DF is the compressive force, and tensile force anyhow FP into APF. Okay, and you can see the centroid of this one is well known, half of DF. So the lever arm will be calculated like D minus half of DF, nothing but 0.5 times of DF. Okay, and the centroid of this one is at 0.42 XU from top. Okay, so that is how it is being taken. Okay, and this force is again same as the earlier case. Now how you write the formula for finding mu for this case? Okay, so it is like FPU APW. FPU APW is the force, lever arm again same D minus 0.42 XU is the lever arm, plus this is resistance from web. Similarly, you have to write a formula for resistance from flange. So what is resistance from flange? 0.45 FCK B minus BW DF into D minus 0.5 DF. Force into lever arm. Okay, compressive force into lever arm D minus 0.5 DF. Okay, this case the code will not talk about, so you have to develop the formula on your own. Okay, code only gives you the first case of uh, uh, the neutral axis falling in the flange. Okay, right. So where APW is nothing but area of pre-stressing steel in web, APF area of pre-stressing steel for flange, and thickness of flange. So to get you know, you will be knowing only AP value. So how you get this no APW value? By knowing APF. How you get APF is from equating compressive force is equal to tensile force. So APF into FP, that is stress in steel into area of steel in flange, is equal to tensile force, which is equal to compressive force. Compressive force is taken from this one, 0.45 FCK B minus BW DF. This is compressive force. So AFP, you are now bringing this towards the denominator, that you will get APF value. So once you get APF value, substitute it here, you know total area, so then you will get APW value. Okay, so that is how it is. APW is equal to AP minus APF. Okay, now again to substitute FPB value, nothing but FPU, and XU value, you have to again read the values from the table. Okay, as I said, the code use FPB as the symbol, whereas the textbook use FPU. So you have to accommodate that symbols, notations between the textbook and the IS code. Okay. So again, you have to read for effective reinforcement ratio, APW. Now you have to use little change. You have to change the formula. You see the table where FPU is there. So write the same notation. As you see, the textbook use only FP. And now it is BW, not B. That is only for rectangle, and FCK. So the change in the formula is, instead of AP, you are using APW, web area. Okay, APW, area of steel in the web, and BW, width of web, FPU, characteristic tensile strength, D remaining all same. So except total area of steel, now you have split the steel into two, some portion to flange and some portion to web. Only web portion you have to give it here, and width of web you have to use. For this value, you have to read the values from table. Okay, so this is for no rectangular and no uh, the flange sections where the uh, the neutral axis lies in the flange. If it is falling in the web, if so, instead of APS, you have to use APW, and FPU is as it is divided by, instead of B, you have to write BW, D same, and FCK same. So there is a change in the formula. So use for the third case of where the neutral axis falling in the web portion out of flange, then use this formula. And again, read for a particular value, whatever you get, read it, and FPB and XU, get the values of these two and substitute in this formula. So FPB means FPU in this formula. Okay, and XU substitute for this. Remaining all other are given data. Just substitute all other values. Get MU value, moment of resistance for flange sections with neutral axis falling outside the flange. Okay, so this is how we can read or we can calculate the moment of resistance for three types of sections. One is rectangular, another one is T section or flanged sections, falling neutral axis falling in the flange, and the third case is like the flange sections with neutral axis falling outside the flange. Okay, so these two formulae you have to just to understand what it is and how to use it, how to get the values to substitute. We'll see examples, no issue. And only thing, you have to develop this formula on your own. It is not available in the IS code. Okay, so that is only the first case is available. First two cases, the formula is available in the IS code. It says for other cases you generate on your own. Okay, so that is why we have uh, taken this similar form from the RCC. Okay, right, so you already know how to write the moment of resistance for flange sections with neutral axis falling outside the flange from RCC, right? Okay, right, we'll see some examples in the next session.